Hi, in this lecture I will be focusing on the classifications of system and there are different kinds of properties of the systems. Either it can be a linear or non-linear system, obeying superposition or not obeying the superposition theorem. It can be a kind of time variant and time invariant system, and a kind of linear time invariant and linear time variant system. A system can be a kind of static system exhibiting no memory, or a kind of dynamic system which is exhibiting memory, or it can be a kind of causal system which is taking into consideration the present and past inputs for calculations, or it can be a kind of non-causal systems which is taking into consideration the future inputs. A system can be invertible or in non-invertible, or it can be a kind of stable and unstable system. So these are some properties of the systems, and we will be looking at their definitions and the conditions which are needed for them to pass in order to be in some category of the system. We will see some conditions in a kind of mathematical manner, and we will see what are the conditions for a linear system, a time invariant, or any property of the system. So firstly we can focus on the linear and non-linear system. A linear system is the one which obeys the superposition principle, and for example, we have any kind of system which is having two inputs which are x1t and x2t, and two outputs y1t and y2t. Then for that system to be a kind of linear system, it has to obey this kind of condition in which the two inputs, when they are multiplied by some kind of uh, constant, and they are aggregated together, and then their transformation is happening, and there is a kind of result which is equal to, for example, a kind of x value. And if we do the transformations of the inputs separately and then multiply the coefficients with them and calculate their aggregate, then in both cases the answer has to be equal. If that is the case, then the system is a kind of linear system. So this is a kind of mathematical condition which is needed for any system to pass it, because any system has its mathematical equation, and that mathematical equation has to pass this mathematical condition in order for that system to be a kind of linear, otherwise it is a kind of non-linear system. For example, we have any system which is reflected by the following equation, where yt is the output and x squared t is the input. Because we have the input was about xt, and when input is coming into the system as an input, then there was a block in the system, and the output of that block will be yt, which is the square of the input. So the system is doing the square of the input. So what kind of transformation a system is doing to the input? This is capital T is basically indicating the transformation. So what kind of transformation the system is doing to the input? It is taking the square of the input. So we have to, for that equation, we have to prove it for linearity or non-linearity. We have to see this equation, and we have to put the values in that equation and see that either that equation is obeyed or not. So let's suppose we have two inputs of this kind of system. Then this kind of system is doing what? It is taking the square of the input, which is indicated by the transformation. So there will be x1 square t and x2 square t. And when both these values are put in this equation, we get this kind of response. And for that equation, to be calculated on the left hand side, because on the right hand side would already got the answer, and for the left hand side we have to take the answer now. So we take the left hand side, and we see that if what kind of transformation this kind of system is doing, it is taking the square of the input. So this is an input, and when its square is taken, it will be like that, whole square coming outside. And then we have a plus b whole square formula, which is needed to simplify that equation. And we see that this left hand side is not equal to the right hand side, so we can say that this system is a kind of nonlinear system. Then we have another system which is explained by this equation, which is telling us that we have an input xt, and which when comes into the block of the system as an input, then the output will be yt, which is equal to the input as well. So the system is doing nothing but to reproduce the input on the side of the output. So again we are putting the values in this equation to see either that system is a kind of linear or non-linear system. So first we take the right hand side, and we calculate the entities that if let's suppose we have this kind of system has two inputs x1t and x2t, then what kind of behavior it is doing to the input? It is just reproducing the input on the side of the output, and we have the inputs which are coming over here. And when we put these values on the right hand side equation, which is a mathematical equation which is needed to be proven in order for the system to tell either it is linear or non-linear system, then when we put the values, then we get this answer. Now we have to take the left hand side of the equation, and this input is just reproducing, this system equation is just reproducing the input on the side of the output. So it is doing a transformation of, when we do the transformation of this equation, then it will be again this equation, and it is equal to the right hand side equation. So we can see that this system is a kind of linear system because it is obeying this equation. Now this equation is basically a mathematical equation to prove the superposition. And superposition is what it is telling us, that if we have any two waves, and we have uh, noises, or we have ripples, or we have variations in any two waves, and when we take the aggregate of those two uh, waves, we have a combined wave. So the superposition is telling us that the combined effect of the noises, which is for the individual waves, has to be equal to the aggregate wave noises. So this is what superposition is telling us. But anyways, we do not have to uh, uh, go into the definition. We just have to deal with the mathematical equation, and that's all. We have any kind of system which is explained by any equation, and we have to see that for linearity it is obeying this condition or not obeying. If it is obeying this condition, then the system would be linear, otherwise it will be a kind of non-linear system. Now we can see uh, about time variant and time invariant system. A system is said to be a time variant system if its input output characteristics change with time, and if they are not changing with time, then the system is said to be a kind of time invariant system. So if the characteristics of system are changing with time, then it is a kind of time variant, and if they are not changing, then a kind of time invariant system. For that to prove, we have to obey this condition. If this condition is obeyed, then the system is a kind of time invariant system. Here we have yn comma k bracket close bracket open from here, and then we have this y into bracket n minus k into bracket close. This y comma n yn comma k is further elaborated by this, that we have to, when we have to do the calculation of y and k, then we have to just replace n with n minus k values in the time bracket, not outside the time bracket. So this is what is indicated by yn in comma k. It will be more clear when we will see the below definition, the below examples. So we have to prove this condition in order for the system to be time invariant. And if we have any system which is elaborated by the following equation, then we can have to calculate first y and k and then y n minus k. So firstly we calculate the y and k, which is equal to transformation of x into n minus k, which is just telling us to replace the time bracket values of an equation. So when we do this kind of transformation for the above equation, we get this, which is we replace the time values, which is for the discrete case the sampled values from n to n minus k for these two, and we get this kind of answer. And now we have to you have to do the rectification of this. This is y n minus k, it is not y n comma k. So when we calculate the y n minus k, which is this one y n minus k, rectify it, then we have the same answer, that we replace the n values with the n minus k values in the whole equation within the bracket of the time uh, n as well and outside the bracket as well. So there is no value of n outside the bracket, only the values of n are within the bracket. So when we replace n by n minus k, we get this answer, which is equal to the left hand side, which is y n k. So this is y n k and this is y n minus k. So this condition is being proven, y n k is equal to y n minus k, so it is a kind of time invariant system. Now we see another equation of the system, which is this. Now we have to calculate again y n k, and this is y n minus k, rectify it again, this is y n minus k. So when we take the y n k of the above equation, then this is equal to t square bracket within which we have x into n minus k. Then we have to replace only the values which are coming within the brackets with n with n minus k. So this is this answer, only the values within the bracket of the n are replaced from n to n minus k. And when we calculate the y n minus k, this is n minus k, then we have to replace all the values of the n which are coming within the bracket as well and outside the bracket. So we get this kind of answer. So it is not equal to y n k, so it is a kind of time variant system. Again we have another example in which there is a system which is identified by this equation, and firstly we have to calculate y n k, and this is y n minus k. So when we do the calculation of y n k, then we replace this n with n minus k, and this is not within the time bracket, it is outside the time bracket, so we do not replace it with n minus k, it will be remaining as n. So when we calculate y n minus k, then we will be replacing all the values of n with n minus k. Then this is the answer, which is not equal to the uh, left hand side equation. So we can say this is a kind of time variant system. Now we will see, we have already seen about the linearity condition, in what cases the system is linear or non-linear, and in what situation the system is time variant and time invariant. Now we have a system which is coupling both these scenarios, which is linear time variant system as well and linear time invariant system. So a system which is satisfying both the linearity and time invariance condition is a kind of time invariant system, and a system which is satisfying the linearity as well as time variance condition, it is said as linear time variant system. So you have to rectify over here variant, and this will remain as it is. There is a kind of mistake in over here, you have to replace it, that a system is said to be linear time variant if it satisfies both linearity and time variance, not invariance. You have to delete this in, And a system is said to be linear time invariant when it satisfies both linearity and time invariance. So we have any equation of the system. Firstly, we have to uh, satisfy the condition of the linearity. The condition of linearity was where it was this condition. We have to satisfy this condition first. So uh, we can go downward. So we have to calculate the right hand side first. What this kind of system equation is doing, whenever a kind of input xn is applied to any box of this system which is elaborated by this equation, then an output of n into xn appears on the output. So if that kind of system has any two inputs, then it will be doing the same to those two inputs with this kind of response, and we place these values of right hand side linearity equation, and on the left hand side, if we take it as an input, then the whole input will be multiplied by n, and we can see this left hand side is equal to right hand side. So the linearity condition has been fulfilled. Now we have to check about time invariant condition. So for time invariant condition, we have to first calculate the y and k, and when we do this kind of, we take this kind of equation, then we replace the within bracket time values, which is n is replaced by n minus k, we get this kind of answer. And when we get y n minus k, then it is the whole values of n are replaced by n minus k. So this is not equal, both left hand side is not equal to right hand side, so the system is time variant, and we can say that the system is linear time variant kind of system. If we have this kind of equation, then we first do the calculation of the linearity condition, and for that, if this system has two inputs x1n and x2n, then keeping into consideration this response equation of the system, we see that the system is taking the square of the input and multiplying it with some n value, and for both the inputs it is doing the same thing, and we put these values on the right hand side equation of the linearity to get this kind of answer. And if we take the left hand side, then there will be a kind of whole square of this equation and multiply by n, and when we open the a plus b square, which is this a plus b square, then we will be getting this kind of response equations. Then it is not equal to the right hand side, which was this one, so the system is a kind of non-linear system. Now for the time invariant condition, it has to fulfill y n k is equal to y n minus k. So when we do the y n k, then it is replacing the within n time values, so n is replaced by n minus k, and what the y n k is replacing all the values of n with n minus k. So these both two are not equal to each other, so it is time variant kind of system. So the given system is neither a linear time variant or a linear time invariant system. It is a non-linear kind of system which is time variant. Now we have another property of the system, which is static and dynamic system. A static system is a kind of memoryless system which is taking into consideration only the present values for the calculation of its output, while a kind of dynamic system is keeping into consideration the present, past as well as the future inputs for the calculation of output of that system, which is a dynamic system. So any equation, if we have to prove that either it is a equation of a static system or as well, or it is a kind of dynamic system, then we can see this example. If this is a kind of output over here, then we can see. So if there is a kind of equation of the system, and we have to tell that either that equation is reflecting a static system or a dynamic system, then we can have to do this exercise. We will be replacing the value of n with 0, and we can see that the 0 is indicating the present value. So we can once see the equation, and we can see if there is no minus 1 or no 1, because 1 2 3 over here will be indicating the future values, and minus 1 minus 2 minus 3 will be indicating the past values, and 0 will be indicating the present value. So if by putting the n equal to 0 and we get just this entity, then it means it is a kind of static system because it is taking into consideration only the present input. Now if we have this kind of system equation and if we replace all values of n with 0, then we will be looking at that it is also having a past value as well as a present value. So this is a kind of dynamic system. And again, if we have this kind of equation and we replace the value of n equal to 0 over here, we can see over here that this output is being calculated by a kind of future value of input as well as the present value of input. So it is a kind of dynamic system. Now we can see about casual and non-casual system. A casual system is one if its response is dependent upon present and past inputs and does not depend on future input. So any casual system is having calculation of the output based on the present and past inputs, and any non-casual system is keeping into consideration the future inputs. So any system equation, if we have like this over here, and if we have to check either that system equation is a kind of casual or well as non-casual system, then we will be replacing the value of n with 0, and can see over here that it is having the output calculated based on the present value of input as well as past value of input. So it is a kind of casual system. If we have this kind of system which is explained by this equation, and if we put the value of t is equal to 0, then we will be having this kind of equation. So we can see over here we have one future value as well as one present value. So it is a kind of non-causal system which is taking into consideration the future inputs only or the present and the future inputs only. If we have this kind of equation and we put the value of n equal to 0, then we can see over here that this equation is giving us the calculation of the output based on the present value of input, the past value of input as well as the future value of input. So output response depend on the present, past and future inputs. So given system is a kind of non-causal system. So we can see over here that all causal systems may not be a kind of static system, but all static systems is a kind of causal systems, because the causal system is taking into consideration the present as well as the past values for the calculation of its output, while the static system is only consisting of the present value of the input for the calculation of the output. And similarly, all the non-causal systems are a kind of dynamic systems, but all dynamic systems may be not a kind of non-causal systems. Okay, we have another kind of system which are invertible systems as well as non-invertible systems. So we have to tell about these kind of systems, but before that I have to be specific about my argument that all non-causal systems are dynamic systems, because all the non-causal systems are taking into consideration the future inputs. The future inputs have to be necessarily uh, available in the equation of the non-causal system, while it is not necessary for a kind of dynamic system. That the dynamic system can, the output of the dynamic system can be calculated based on the present and past inputs or the present and future inputs. So a kind of dynamic system which is having a present and past inputs is not a kind of non-causal system, but it is a kind of dynamic system. So that argument was valid for that condition. Now I will be focusing on the invertible and non-invertible system. A system is said to be a kind of invertible system if the input of the system appears at the output of the system. Like we over here, you can see that we have a diagram of a system, and we have an input coming, and we have an impulse response over here, and we have an output of that system, and we have another impulse response over here, and then we have reproduced the input. So this is a kind of invertible system demonstration. We can mathematically prove this concept as well. We can see that output is based on the input convoluted with the impulse response h1t, and the y1t is equal to xf into h of f. This has to be rectified. You have to rectify it, that this kind of equation, when we do the frequency transformation of this kind of equation, we get y1f into xf multiplied by the h1f, which is convolution in the time domain is the multiplication in the frequency domain. So if we see this kind of box, and we can see that yt is equal to input, which is y1t, which is time convoluted with h2t, which is this one. So we can see that if what is y1t? y1t was xt convoluted with h1t, so we have replaced the value of y1t over here, and we when do the frequency transformation, the convolution is changed to the multiplication operator, and then we can see that if we have a condition that both impulse responses are nullifying each other and the value of 1 is being we get this value of 1 over here, then yf is equal to xf, and when we take the inverse Fourier transformation, then we can see that yt is equal to xt. So it is a kind of mathematical derivation or interpretation of a kind of invertible system, and this is a kind of demonstration of the invertible system. So any kind of system which is not obeying this mathematical interpretation or this diagrammatic demonstration, this is a kind of non-invertible system. Now we will look at the definition of a stable as well as unstable system. Now we have a stable system as well as unstable system. So a stable system is the one which is producing the bounded output for any kind of bounded input. What is bounded input means? It is a kind of finite input, and bounded output means it is a kind of finite output. So any kind of system is said to be a stable system if it is producing a kind of finite output for a finite input. Like we have, for example, this equation, and we have this equation of the system, and we have to tell about that either it is a kind of finite system, a stable system, or unstable system. Then we will be looking at that if xn is equal to unit step function, and when we take the square of that unit step function, then it is a kind of u square n, and the square of the unit step function is always a unit step function. So unit step function is a kind of finite system, finite input as well as finite output as well, because it is within the magnitude of 1, and we have whenever we have a y-axis and we have the x-axis and we have a unit step function, then unit step function magnitude is always equal to 1 and it remains within a finite limit. So it is a kind of bounded input as well as bounded output as well. So we can say that it is a kind of stable system. Then we have when we have this equation and we want to prove that either it is a kind of producing bounded output for any bounded input. If it is obeying that condition, then it will be a kind of stable system, otherwise it will be a kind of unstable system. So we replace the value of xt with ut, unit step function, and we take the calculation. The square of the unit step function is always a unit step function, and we aggregate two unit step function, then it will be a kind of 3 ut. It is a kind of finite system. It is a kind of producing finite input as well as finite output as well, so bounded input as well and bounded output as well, so it is a kind of stable system. Another equation, we have this system equation, which is integral of xt into dt. When we replace the xt with ut, then integral of ut will be a kind of ramp function, and ramp function is increasing linearly to infinite regions, and it has no particular uh, amplitude, and it is increasing with every moment passed, so it is a kind of infinite kind of output, which is a ramp function. So it is a kind of system which is for a finite input, for a bounded input, is not producing a bounded output. It is a kind of producing an unbounded output. So we can say this is a kind of unstable system. This is a demonstration of the Laplace transformation, and which is an imaginary axis, real axis and imaginary axis, and it is telling that for that, if the poles of the system are pointed on the left hand side, it is a kind of stable system. Otherwise, if it is pointed on the right hand side, it is a kind of unstable system. and when the poles are within the coordinate system, it is a kind of critically stable system, but this is not within the scope of this lecture. Thank you very much.